All right, welcome to Talk Tensors, everyone. We love diving into these machine learning papers, and that's exactly what we're going to do today.
It's so true. We like to take these sometimes complex academic papers and try to extract the key insights that our listeners are going to want to know.
Yeah, because you don't always have time to go through and read these papers.
Totally. Who has the time?
And they can get pretty dense and technical, so today we are going to tackle a really interesting one. It's called Mellow, a small audio language model for reasoning.
Oh, yeah.
And this title is, I think, a little bit misleading. So we're going to kind of dive into the details of how this model works and what it accomplishes, because it's pretty surprising.
Yeah, this deep dive is all about how a relatively small AI model, as you said, can achieve some pretty strong reasoning abilities over both audio and text. And we are going to explore why this is significant for the field of machine learning.
So our primary source here is, of course, the paper itself, Mellow, a small audio language model for reasoning. So without further ado, let's get into it. So what exactly is Mellow, and why is it causing a stir in the machine learning community?
Mellow is a small audio language model, or ALM, and it's designed specifically for reasoning. Now, in machine learning, typically, bigger is better.
Yeah.
To achieve better performance, especially on more complex tasks like reasoning, you typically need large models with billions of parameters.
Right. So what makes Mellow so interesting in this context?
While Mellow performs exceptionally well, even though it's relatively small, it achieves state-of-the-art performance among other small ALMs. And in some reasoning tasks, it even surpasses much larger models. In fact, the researchers provide a striking comparison. Mellow scored 52.11 on the MMAU benchmark. Now, that number by itself may not mean much to you, but consider this. It's comparable to the much larger Qwen 2 audio model, which scored 52.5.
Right.
But here's the key. Mellow achieves this using 50 times fewer parameters, and it was trained on 60 times less audio data, around 152 hours for Mellow, versus much more for Qwen 2 audio.
Wow. So that's that's a big difference in the amount of data and model size for basically the same level of performance. So why is that significant for our listeners?
The potential impact of small reasoning-capable ALMs like Mellow is huge, especially for applications on edge devices. Think about your smartphone, smart home devices, embedded systems. These all have limited computing resources. Having powerful AI that doesn't need massive processing power opens up a whole new range of possibilities for how we use machine learning in everyday life.
Makes a ton of sense. So they didn't just train a small model on a small data set and hope for the best, right? What's the secret sauce here? How did they actually get Mellow to reason so effectively?
It's not just about the scale. A crucial part of Mellow's development was a new dataset called Reason AQA that was created specifically to train models in audio-grounded reasoning.
So what makes Reason AQA special?
Reason AQA is a mix of existing data sets, about 30% of it, and 70% of it is data they generated synthetically.
Synthetic data. To train an audio reasoning model, how did that work?
They started with audio descriptions from two well-known datasets, AudioCaps and Clotho, and then they used large language models, LLMs, to generate detailed multiple-choice questions based on these descriptions.
So the LLMs were basically creating reasoning challenges based on text descriptions of audio.
Exactly. And these questions focused on various aspects of the audio, like what events are happening, what objects are present, the overall scene, specific properties of the sounds, the semantic meaning, and even potential emotions evoked by the audio.
So this allowed them to create a large data set that was tailored specifically for reasoning about audio.
Exactly.
Clever. And how did they actually evaluate Mellow, to see how well it could handle different kinds of reasoning?
They evaluated it on a diverse set of tasks, including fundamental audio understanding, deductive reasoning, drawing logical conclusions from the information, and comparative reasoning, like identifying differences between two audio inputs. Importantly, they tested it on both data that Mellow had seen during training, as well as completely new data.
That sounds really thorough. And I bet they didn't just stop at the performance numbers, right?
Of course not. To really understand how Mellow works, the researchers conducted some extensive ablation studies.
Oh, yeah.
So they systematically changed different parts of Mellow's design and training, like the specific architecture, how the audio and language components interact, the methods for creating that synthetic data, and even the type of language model they used.
So by seeing how these changes affected Mellow's reasoning abilities, they could figure out what was most effective.
Okay.
Clever. So to really understand the significance of this paper, let's take a step back and look at the historical context that led to this development. What's the evolution of computational audition and machine listening that brought us to this point?
That's a good question. Over the years, we've seen a transition in computational audition and machine listening. Early on, the focus was on creating models that could perform very specific tasks like, identifying different types of sounds or classifying music genres.
Right, very targeted applications.
Right. But over time, the field has shifted towards building more general purpose models, what we call audio foundation models. These models are designed to handle a much wider range of audio-related tasks.
And how has language become integrated into these audio models?
Many of these audio foundation models now use language as a form of supervision during their training. So they might use techniques like contrastive learning, like in models such as CLAP, where the model learns to recognize when a piece of audio and a piece of text are describing the same thing. Or they might use next token prediction, where the model learns to predict the next word in a sequence given an audio input.
So the model is basically learning the relationship between sound and language.
Exactly.
Got it. And I'm guessing there's been a trend toward larger models and larger data sets in this area too.
Yeah, as with many areas of machine learning, there's been a big push to scale up both the data and model size in computational audition. And this has led to some really big improvements on benchmark data sets. And perhaps even more excitingly, it's led to the emergence of some new capabilities that we didn't really expect.
Like what? Give us an example.
Well, for instance, some models are now able to estimate the overall quality of an audio clip without being specifically trained to do that. You also see improvements in audio text reasoning, and some models are even starting to show signs of logical reasoning abilities like deductive reasoning.
So it's like they're learning things that they weren't explicitly taught just by getting bigger and being exposed to more data.
That's right.
Interesting. Now, the Mellow paper specifically talks about the distinction between understanding and reasoning in audio models. Can you explain that a bit more?
Yeah, that's an important distinction. Understanding in this context is about being able to grasp the meaning and coherence of the input, like knowing what's there.
Okay.
Reasoning, on the other hand, goes beyond that and involves drawing inferences, making logical connections, answering questions that require more than just recognizing elements in the audio.
Okay, so understanding is like knowing what you're hearing, and reasoning is like being able to think about what you're hearing and draw conclusions.
That's a great way to put it.
So how do researchers typically try to improve reasoning in audio models?
Well, there are two main approaches. The first, and perhaps the most obvious, is to expand the coverage and diversity of the training data. The idea is that if you expose a model to more audio examples and scenarios, it'll have a broader base of knowledge to work with when it comes to reasoning.
More data, the classic solution.
Right.
What about the second approach?
The second approach is to actually enhance the model's inherent reasoning ability itself, regardless of the data. So this might involve exploring new model architectures, using different learning techniques, or applying specific post-training methods.
So instead of just giving the model more data to learn from, you're trying to make it smarter in how it uses the data it already has.
Exactly. And the Mellow paper emphasizes that most previous work has really focused on that first approach, scaling up the data. Mellow's work is notable because it explores that second path, trying to improve reasoning independently of massive data sets.
Okay, that makes Mellow's achievement even more impressive then, performing so well with relatively limited data. So let's talk about the novel notions section of the paper. What are some of the key extension topics or deeper analyses that Mellow brings to the table?
One interesting point they explore is Mellow's reliance on the language model component compared to some previous audio question answering models, or AQA models. There was a concern that some of these AQA models might not actually be listening to the audio that much, and instead were relying heavily on the language model to answer questions.
So they're essentially cheating.
Sort of, yeah. To test this in Mellow, the researchers did a clever experiment. They replaced the actual audio input with random noise.
Okay.
And they observed that Mellow's performance dropped by about 13% when they did this.
So it's definitely using the audio information then.
It is. But for context, larger multimodal models like Gemini 1.5 Pro and Qwen 2 Instruct show an even larger drop when you do this, indicating a stronger reliance on the audio. The researchers attribute this difference to the fact that speech-related tasks make up a big part of the benchmark. And Mellow, trained on less speech data, doesn't perform quite as well on those tasks. It might be relying more on the language model in those instances. So while Mellow is using the audio, there's still room for improvement in how tightly the audio and language processing are integrated.
Makes sense.
Yeah.
What other interesting analyses did they do?
Well, they did a deep dive into Mellow's performance on the MMAU benchmark, breaking it down by the difficulty of the questions. And it turns out Mellow actually did best on the medium difficulty questions.
Interesting.
Yeah. It suggests that its reasoning capabilities are strongest when the task requires more than just basic recognition, but it's not super complex either.
So it's better at that sweet spot of kind of moderate difficulty.
Right. They also looked at specific categories of questions within MMAU, and they found that Mellow excelled at tasks that involve identifying the source of a sound, interpreting ambient sounds, and music texture. But it struggled more with speech-related tasks, again, likely due to the lack of speech data during training.
So that points to another area for future research.
It does.
What about deductive reasoning? That was a big focus of the paper.
Yeah, Mellow showed really strong performance on deductive reasoning tasks using the audio entailment benchmark. In fact, it even outperformed much larger models in some cases.
Wow.
Yeah. It was particularly good at determining whether a given statement was definitively true or false based on the audio. But they did notice that Mellow was a bit weaker when it came to classifying neutral hypotheses, like situations where the statement might be plausible, but you couldn't say for sure if it was true or false based on the audio alone.
So it had a harder time dealing with ambiguity.
Yeah, exactly.
What about comparative reasoning?
On the audio difference benchmark, where the model has to distinguish between two audio inputs, Mellow was again competitive. It did particularly well on Tier 1 questions, which require short answers, and Tier 3 questions, which call for more detailed explanations. But it lagged a bit behind a larger model, QAS, on Tier 2 questions, which require brief answers.
Any ideas why?
The researchers think this might be because Tier 2 questions are more linguistically complex, maybe using more general language and less specific audio descriptive terms. And Mellow's smaller language model might just not be as adept at generating these kind of nuanced responses compared to a larger language model.
So even though it understands the audio well, the language generation can still be a bottleneck for certain types of reasoning.
Exactly. The paper also shares some insights from the ablation studies. They found that fine-tuning the entire language model with a small, either a linear or a two-layer nonlinear mapper, connecting it to the audio encoder, was more effective than using techniques like prefix tuning or LoRa adaptation for the specific architecture and dataset.
Okay, interesting. So that's a practical tip for people building similar models. What other interesting findings came out of those ablation studies?
Well, they found that using a better pre-trained language model, specifically small LM2 instead of GPT-2, led to significant improvements on open-ended reasoning tasks.
So having a smarter language model as the foundation really helps.
It does. They also found that better unimodal audio representations led to better reasoning performance. So using a more powerful audio encoder, like HTSAT, for example, gave the language model a richer understanding of the audio, which helped with the reasoning.
It's all connected.
It is. And finally, they highlighted the effectiveness of using reasoning-focused synthetic data like Reason AQA. They even found that incorporating expert-written questions into the data generation process was particularly beneficial. So this opens up some interesting possibilities for how we can design synthetic datasets to train these models even better.
Wow, so Mellow is more than just a model. It's really a collection of insights about how to build effective small ALMs for reasoning.
That's a great way to put it.
So what's the main takeaway for our listeners here?
The key takeaway here is that small audio language models can be surprisingly good at reasoning. This opens up a lot of possibilities for deploying sophisticated AI in environments with limited resources.
And for folks who want to dig deeper into Mellow.
The good news is that the researchers have released the model checkpoints, the Reason QA training data, and all the evaluation code publicly, so anyone can explore this work in more detail and build on it.
Excellent. So as we wrap up this deep dive, here's a final thought for our listeners to ponder. Given Mellow's success, what other areas of AI might benefit from a similar focus on building smaller, more specialized models? Instead of just always chasing bigger and bigger models, could we be moving towards a future where reasoning efficiency is just as important a design goal as raw performance?
That's a great question, and it's something worth thinking about.
Indeed. So thanks for joining us for this exploration of Mellow and audio language reasoning. We encourage everyone to check out the paper itself and the related research to learn more.
Absolutely. And until next time, keep exploring the fascinating world of machine learning.
See you next time.